Hey everyone, it's Dr. Coggins. Today we're doing experiment 9, and this is electrons are into bondage. They like to bond with other atoms. So we're going to first do a little bit of review, which is nice because this lab covers 2 of our chapters all at once, although it is a long one. So Lewis dot structures, again, are based on Roman numerals and valence electrons and connecting at single dots only. So remember, you can determine valence electrons by looking at the top of their families for their Roman numeral or their group number. Just remember, if you're using the 1 through 18 numbers, to subtract 10 from 13 through 18. It's 1 through 8 that we care about, and it's all the top tall families. So the first thing I'm going to do is practice just recognizing how many electrons are we dealing with. So let's do a few together, and then I'll let you do the rest. So as we look at examples here, we just need to remember that it's all about the Roman numerals. So for bromine, it's in the halogen family, that's group 17, but also Roman numeral 7. So since there's 2 bromines, we're going to say 2 times 7 electrons. 7 electrons is the Roman numeral. So again, this is Roman numeral VII, and 2 times 7 is 14 electrons. And that's what we want. Very similar as a bunch of the others. Let's do some of these down here because they have charges. So here we have hydronium, which is an ion we'll use in the acid-base chapter. We have 3 hydrogens, so that's 3 times 1 electron. That's because this is Roman numeral 1, family 1, it's above the alkali metals. And then we have oxygen, which would be 6 more electrons. There's only 1 of those, so we don't have to multiply. But then notice we have this positive 1 charge. That positive 1 charge means subtract 1 electron. So we have 3, we have 6 more makes 9, then we subtract 1. We get magic number 8. The octet is the favorite for everybody. Let's do one more and then I'll let you try the rest. Let's do a negative one. So here we have nitrogens with a negative charge. This is nitrite. So nitrogen is 5 electrons. That's because it's in Roman numeral V, just like this was in VI up here. So again, we're going to use that again because there's 2 oxygens here, so there's 2 times 6 electrons. Same Roman numeral, same number of electrons in group 16 over Roman numeral 6. Notice we have a negative 1 charge here, so negative is the charge of an electron, so we're going to now add 1 electron. So we have 5, we have 12, and we have 1 more, and that gives us 18. So take a few minutes to try the rest. Just remember, positive charges take away electrons, negative charges add electrons. Alright, so as we move on to page 48, we're looking at Lewis dot structures based on those very same Roman numerals from the front page. So remember, 1 per side. So if you're lithium, you're going to have 1 electron because you're in Roman numeral 1. If you're beryllium, you're going to have 2. Boron, you're going to have 3. Carbon with 4. Nitrogen with 5. Oxygen with 6. So again, 1 on each side. Fluorine with 7. And neon, it has what everybody wants, and that's the octet magic number 8. So as we do this, we're going to go down and make things symmetrical and do exactly this, but we're going to connect the single dots only. The single dots are called unpaired electrons. These paired electrons, these lone pairs, are left alone, so don't use those in anything that we do coming up. So one of the first things I'm going to do in order to make it a little bit easier on you is draw these out symmetrically first. So carbon with 2 hydrogens and 2 bromines. Molecules are symmetrical, and we're made up of molecules, so that's why we look symmetrical in a mirror. So then we have a carbon with 2 hydrogens and sulfur. We have 2 carbons, halogens and hydrogens never in the middle, so those are on the edges. The reason we don't put hydrogens and halogens in the middle, go to the top, they can only share once as a halogen, they can only share once as a hydrogen in the same family as lithium. So keep those out of the middle. We have phosphorus with 3 fluorines. And then selenium with 2 hydrogens. So I'm going to pause the video and give you a moment to look at the top, find the family and add that number of electrons. Alright, so hopefully you've tried that. Let's do it real quick together. So here's a halogen, give it 7. Let's find some other halogens, working backwards from the noble gases. We have some chlorines here. They get 7. We have some fluorines here. They get 7. Notice I'm putting the single dots towards the middle. That way they're easier to connect. So there's all of our halogens. Let's go now to the chalcogens, which have 6. So those are the oxygen family atoms, and here's a sulfur. So give it 6. Here's a selenium. Give it 6. So far, so good. Now let's move over to the pnictogen family, the nitrogen family. Nitrogen, phosphorus, here's a phosphorus. Give it 5. And then now carbon family. Carbon family has 4. So silicons and carbons, here's 4. On carbon, here's 4. On carbon, 4 on carbon, 4 on carbon. And then we don't have any boron family atoms or beryllium family atoms. We do have a lithium family atom, and that's hydrogen. They get 1. So this is a perfect time to pause the video again, connect the single dots only. Alright, so as we connect the single dots, we should get 1, 2, 3, 4 single bonds. That's carbon's favorite type of bonding. 4 bonds, no lone pairs. We do the same thing over here, 1, 2, and then 3, 4. So we get this double bond up to the sulfur. And it's okay if you were to draw through the atom, it just looks a little weird. So again, 4 bonds to carbon, 4 bonds to carbon. We get 4 bonds to carbon now with a triple bond by connecting the single dots there. We get nitrogen family atoms with 3 bonds, and this lone pair up top. And then we get selenium with just 2 bonds, 2 lone pairs, as expected for that family. So take a minute to count up your electrons and put in your valence electrons. You could have done that before, but a good way to check them is to count them up. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So do that for the rest of them now. Alright, so as we move on to page 49, we're getting to some of the rule breakers. So what we just did, connecting the dots, that works about 95% of the time, and in reality, in Intro Chem, that's probably good enough. What we saw for the carbon family is it like 4 bonds, no lone pairs. The nitrogen family, like phosphorus, like 3 bonds, 1 lone pair. Oxygen family atoms, like selenium and sulfur, they're going to like 2 bonds, 2 lone pairs. And then halogens that we never put in the middle, they're only going to like 1 bond, 3 lone pairs, and we don't deal with noble gases. They already have what they want. So the problem that we have down at the bottom of this page is connecting the dots is going to fail. So we're not even going to try it. We're cutting to the chase, and we're going to do exactly what we did last time, at least our first step. So as we go down, we want to make it look symmetrical one more time. So in this case, because it's a rule breaker, we are going to put chlorine in the middle because we need it to be symmetrical. Phosphorus in the middle to be symmetrical. Oxygen in the middle. Hydrogen can never be in the middle whatsoever. Here we can't really make it symmetrical. We can go up and down and make it look somewhat symmetrical. Nitrogen with 2 oxygens, nitrite. So there's our first step, make it symmetrical. That's going to work with connect the dots or with this rule breaking kind of scenario. The next thing we're going to want to do is find the valence electrons. So with chlorine at 7, we have 2 oxygens, 6 each. We also have a -1 charge. We add that together. So we get 6 plus 6 plus 7 plus 1. We're going to get our 20. So take a minute to find the valence electrons for the next, and then we'll come back. Alright, so should have found those valence electrons based on the Roman numerals, and then adding in those extra electrons for negative charges, taking away electrons for positive charges. You had a little bit of both in this situation. So instead of connecting dots, because we already said it was going to fail, there's 2 golden rules to always follow. Make sure every atom has 8 and hydrogen 2, and then only use the electrons that you have. It's kind of like a puzzle. Here's the puzzle pieces. Give everybody 8, and you'll never miss any problem, easy or tough. So let's try that with this one. We have 20 electrons, so the easiest thing to do is connect them. So that's 2 electrons, because those would be connected dots. 2 electrons, so there's 4. 6, 8, 10, 12, 14, 16, 18, 20. Has 8, has 8, has 8. We're done. So even though it's a rule breaker, it can still be done rather quickly. So let's try that again. For this one, we have 32. So 2, 4, 6, 8. So far, so good. But 8 is not 32, so we need to keep going. So 8, and then now 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Perfect. So take a minute to try the rest of them, and we'll come back. Because these are the tough ones, I'm going to keep working through them. You're not going to see these too much in Intro Chem, but they are often just enough to be that thorn in your side to keep you honest about connecting the dots. So here we have 8, so 2, 4, 6, 8. So far, so good. Here's a little bit trickier. We need 10 electrons between 2 atoms. So that means there's going to have to be a lot of sharing. The most sharing we can do is 2, and then 4, and then 6, and then 8, and then 10. It's a little bit tougher there to think about how it has to go together. Oftentimes students would end up here. They would say 2, 4, 6, 8, and then they'd have 10, and then they'd be out of electrons. So when that happens, just remember that you can share these back, and that's how we end up with this answer. So anytime that you run out, you have to share back to the middle, so that everybody has 8. That's going to happen over here with 18, so 2, 4, 6, 8, 10, 12, 14, 16, and 18, nitrogen's not enough. So one of these, doesn't matter who, that's called resonance, one of these has to share back to the middle. So it doesn't matter which one we pick, we can pick these. If we share this back to the middle, now it's going to be this structure with a double bond instead. So anytime that you have not enough electrons, you have to share back to the middle. And that happened with carbon monoxide and with nitride here. Let's keep moving forward. Now we're finally into our shape chapter. Everything that we've done previous to this has been from our previous chapter. So this chapter is going to be more detailed on how to recognize first Lewis structure, but then the shape that corresponds to it. So here's our summary. This is a great table to use in the homework for the shape chapter. So as we do this, we need to think about who has or prefers what. Steric number is a definition we see in the notes. Steric number is this direction idea. It's how many electron groups do you have. So if you have 4 directions, it's kind of like a 4-way stop. You can go left, right, forward, or in reverse. Here you only have like a 3-way stop from your center atom. So you can go left or right or backwards. And then here you can only go forwards and backwards. So typically single bonds sit in this category. They're going to have 3 choices in the end. And it really depends on which family as the prediction of what the answer might be. Here you're going to have a double bond somewhere, so don't even use this if you don't have double bonds. And then typically here 2 double bonds or a triple bond, you'll be in that kind of category. So in that 4 category, we call that tetrahedral. Tetrahedral just means it looks like a tetrahedron, which is kind of like a pyramid. Tetrahedrals have 4 even sides, and that's going to happen with carbon with 4 single bonds, 109.5 angle. Pyramidal is going to be just like tetrahedral, but it's going to be a little more squished. It's going to have a kind of flatter base because of its lone pair. And that typically happens with nitrogen. Notice we lose that 2 degrees in angle. And then here when we have 2 lone pairs, we're going to be bent, and that's going to happen to a 105-degree angle for the oxygen family that has extra repulsion between lone pairs. Double bonds are going to make a flat triangle, so we call that trigonal planar. It's going to be a 120 angle, so if you do a donut in the parking lot, that's 360. That's cutting this 3 ways. Double bond and 2 single bonds typically. If there's a lone pair instead of a single bond, you're going to go to bent. This is a very similar kind of bend here, just at a different angle, and we'll see examples of that. The easiest by far is a straight line, and that's going to happen with 2 double bonds on the same atom or a triple bond, or maybe just 2 atoms with a single bond between them. So we're going to do the exact same thing that we just did earlier. We're going to go down to this lower page, try to keep this chart together best we can, and let's make our pattern of atoms symmetrical best we can, and then we'll come back. Alright, so we got them all symmetrically laid out. The only one that's going to cause you an issue is ozone. ozone is a rule breaker, you're going to have to use the previous method where you find the valence electrons, which is 18, and then give everybody 8. So here's fairly easy to just cheat off the chart. We know that the carbon family atoms are going to have 0 lone pairs and 4 bonds, so 1, 2, 3, 4 bonds as expected. Nitrogen family atoms are going to have 1 lone pair. Arsenic sits in that family, and 3 bonds. Halogens aren't up here, but if you remember from the previous page, they're going to like 1 bond, 3 lone pairs. Just like they will over here. So whether you use the chart or connect the dots, these would work either way. Carbon likes 4 bonds, so when you only have 3 atoms, that requires a double bond. Oxygen's like 2 and 2, that's up here. Here it's not going to work, but again, we now have 18 total, so 2, 4, 6, 8, 10, 12, 14, 16, 18. And then HCN, carbon likes 4 bonds. You can only have 1 hydrogen. Nitrogen likes 3 bonds, 1 lone pair. So using just this information here, we can get through most of those answers without too much trouble. Now we want to think shape. The EPG is here. This is the category of shape, and then the molecular shape is here. There's 2 categories. In your homework, we're looking for this answer, but this category helps us narrow down our choices to that answer. So if you look at this group here, you'll notice that it has an up, a down, a left, a right. So it's kind of like a north, south, east, and west. Here we have the same thing. Just remember that lone pairs matter. We oftentimes draw little p orbitals around them, so those dumbbell-shaped orbitals. If you have 2, you have 2. So whether you have 3 and 1 or 2 and 2, this is still 4. So for all of these, we have 4 directions, category of 4. And that's important because that puts us in that category of these kind of answers. So if you're silicon, you're in the carbon family, so we'd expect tetrahedral. And because we're in that family and we stay with 0 lone pairs, 4 bonds, we stay tetrahedral. If you move over to pyramidal in the nitrogen family with arsenic and phosphorus, you're going to expect 1 lone pair and 3. So you might be tetrahedral because all of these are in that same category together. But notice now we don't have 4 bonds, we have 3 and 1 lone pair, so we're going to go to pyramidal instead. And then lastly, for oxygen families, when you have 2 and 2, you're going to go bent. So to show you what that looks like, the silicon atom is the black atom, and notice we have 4 hydrogen atoms attached. And notice from the camera angle, we do have a hydrogen forward and a hydrogen backwards. When we see that in the homework, forward is a dark wedge, backwards is a dashed line, kind of like in a 3D movie. So the same thing would be for our little arsenic triiodide molecule. Notice it looks very similar. This little hole is just representing the lone pair that we can't see, that we can't attach. And notice it too has a forward and a backwards. So it too is going to have a wedge and a dash. And then lastly, so let's put these in order. Lastly, what we're going to see for this sulfur dibromide molecule is when this happens, something unique happens, and 2 lone pairs are going to cause it to do something unique, and that's really just not stay straight, but bend. And when you're bending kind of in the same angle almost as the other 2. You just have a lone pair up and down. So even here we can have a wedge and a dash because those are actually bent away from one another while the lone pairs are in the plane. So that's a representation of the same family. They all represent this family of 4. Let's move over to where we have a double bond. If we have a double bond, we're in the double bond category. Notice we have an up, a left, and a right only. There's no 4 directions. There's no 4 steric number. It's a 3 steric number, so we're in this category. We have a double bond somewhere. So we're going to be trigonoplanar. And we're going to stay trigonoplanar as long as there's no lone pairs. And again, both of these have double bonds, so both of these are in that category of 3. But this one has 4 bonds. When you have 4 bonds, you stay trigonal planar. And what we learned in class is when you have lone pairs, you get extra pushing, so you're going to go from trigonal planar to bent if you have one lone pair, and that's the case here. So here's our formaldehyde molecule. Notice that double bond. Notice that it is perfectly flat, and it shapes what looks like a triangle. And more importantly, as we look at that example, we see ozone, which is a rule breaker. It has the same relative shape. So it's bending together, and it just has a lone pair up top, so it's actually bending together more so than the other one. So lone pairs matter. Turns out they matter even more. So these are going to kind of squish down more than what we drew it. Definitely not linear. That's what we want to stay away from. The last example has a triple bond. Triple bond's always going to be linear and stay linear. So again, this is the category of 2. Had them in perfect order on purpose to give you some comparison. So here's the hydrogen cyanide molecule, or hydrocyanic acid. Notice triple bond. It's going to be straight as a peg, completely linear, completely straight, and this finishes this page. So take a minute to look over that chart, and remember the molecular shape is what we're most worried about in the homework. Alright, so as we move along to page 51, this is practice with polarity. We did polarity in the previous chapter, and we do this in the shape chapter as well. So we see this polarity table in the textbook and in the notes, but what we see it for our exam is this larger one. Same thing, same idea. This is the one that you can use on the exam with your periodic table. So as we do this, we remember that 0.5 or larger is our definition for polar, and less than 0.5 is non-polar. We see that in a lot of chapters coming up, definitely the next 3 or 4 chapters in a row. We're going to still continue to use that. We're not really dealing with anybody over here. We're really dealing with hydrogen versus a lot of these in this upper right corner. And we'll do that at the bottom. Just remember, these guys are the biggest bullies. Fluorine, the biggest bully at 4.0. So subtract these 2 numbers, is it 0.5 or larger? So as we go down here, we have fluorine, and that's 4.0. It's the biggest on our chart. So we're stealing that up here. And then we have hydrogen at 2.1. So subtract 2.1, and you get 1.9. So then you have to ask yourself, is 1.9 larger than 0.5? And when you realize that it is, definitely larger. This is a very polar bond, something we call hydrogen bonding later, just like NHs and OHs. So take some time, find the numbers at the top, subtract, and complete this section. So again, bookmark this page 51. It's going to be important for a lot of the labs coming up. Definitely pay attention to those upper right corner atoms and then hydrogen in particular. But also keep this page handy for our remaining part of our lab, because we're going to look at atoms and how they feel as a result of electronegativity. So when we look at something like this, we see hydrogen with a 2.1, chlorine with a 3.0. It has a pull towards chlorine because chlorine is the bully. That 3.0 versus 2.1 difference is 0.9, significantly polar towards chlorine. We draw a dipole when that happens. This little positive end of the dipole is the positive feeling atom. The arrow is pointing to the negative, or in this case, electronegative bully, so it feels partially negative, and that's exactly what we want. So as we practice in this lab coming up, we're going to find the valence electrons first. Did that on the very front page of this lab. Just get a lot more practice coming up. We're going to draw the 2D Lewis dot structure second. We're going to think about it in 3D with our model kits. And then lastly, we're going to think about electronegativity and polarity as we practice more. So try to get your pages organized, and we're going to come back for page 53 to do all this practice all at once. Alright, so in this lab we're going to use model kits. Unfortunately you guys don't have those at home, but I've made all of them for you. So we'll skip through as we see some of them. I'll walk you through a few examples from each page, and then you'll be able to check the answer key eventually to see if you're on the right track. But we want to get you the process down first. So starting with valence electrons, do exactly what we did for our first page here. So here we have 2 times Roman numeral 7, and that gives us 14 electrons. So take a minute to do this on all pages, 53, 54, and 55. So do that now, hit pause, and we'll come back. Alright, so now we're going to do the second column through the entire lab to save time. So notice with this one we have 2 times 7, so make it symmetrical. Give in your electrons and connect the single dots only. So do that for all the 2D structures on the entire lab. Hit pause and we'll be back. Alright, so hopefully you spent some time doing that. I got overzealous on a few, so you might see a little white out because I knew the answer and was writing it down, not thinking that I wanted it to look like what you would see if you were doing it symmetrically. But in any case, we're going to now plug in the model kits. So as we look at these, see if there's a major difference between what we see and what we'd expect. So here's 2 iodine atoms, and really that's just the same answer. There's nothing forward or backwards here. It's just a straight molecule. What's unique about ICL is it's really the same halogen family, but now we have a smaller atom, chlorine, compared to iodine, but really nothing different about 2D versus 3D there either. It is unique with the next one though, that we do have a shape that is not perfect. It doesn't look like a cross like we see. Looking from the camera angle, we see this chlorine in back, this chlorine in front, and then these 2 in the same plane. So let's try to draw that with carbon here, 2 chlorines in the plane. And then now we have one at the camera and then one away from the camera. So towards is a dash, like a bold dash, a bold wedge. And then that dotted line backwards represents behind. And there's a better representation 3-dimensionally of this model kit. As we move on to the next one, it looks like it's straight across, but definitely not the case because nitrogen has this little arms wide open. So if we hold it to the side, we can better draw it. Notice the hydrogen coming at the camera angle and then the one going away. So we have the wedge, the dash on those hydrogens. We have the oxygen over, but then the hydrogen down at an angle. And don't forget that lone pair is going to matter for its shape. Here we have 2 lone pairs, one will be forward, one will be backwards. So we can kind of illustrate that with a dark lone pair, and then this dotted lone pair is forwards and backwards there. So there's 2 shapes to worry about for this particular molecule. And the last one on this page is, looks a lot like methane. Looks a lot like carbon tetrachloride above. Pretty much identical in the shape. So same idea, wedge forward, dotted backwards, 2 in the plane together for ammonia. So here's those in order as you think about it. Try the next page as we practice more. All right, as we move on to double bonds, let's look at our model kits. So here's oxygen. So nothing too special about it. It stays perfectly flat and in a straight line. We look at ethylene, which makes polyethylene in a later chapter. It's also the molecule that makes fruit ripen. So this blows around an orchard, tells other fruits to catch up. So you can wrap brown paper bags around fruit, trap this molecule, and make it ripen faster as well. So notice it's pretty much like we have drawn in the 2-dimensional structure, so even that doesn't really change. This one here looks like it's straight in a line, but it does have lone pairs, so notice when we make the model kit, it definitely has some bend, which gives away some of its answers. So let's try to draw what we see. We have this hydrogen going up to oxygen, over nitrogen, double bond down. There's a double bond there. We have this lone pair that we can't see going forward and backwards. And then we have the lone pair that's flat with nitrogen. This next one is pretty unique. It's called formic acid. It's used in bee stings and fire ant bites. So this is the molecule that interferes with your nervous system, makes it burn when that sting gets you. So this is the acidic proton that we'll talk about in a later chapter. If you take this hydrogen off, pain goes away. Now you make the formate anion that doesn't have any sensation to our nerves. So a couple of household tricks for this particular molecule is, say, baking soda or nicotine. Those bases can neutralize this hydrogen, make the pain go away. Lots of other household remedies as well. But in any case, it does have this kind of zigzag pattern that we'll see in the organic chapter later in experiment 10. So notice we have hydrogen up to carbon, double bond up, oxygen down, hydrogen up. Oxygen has a lone pair forward and a lone pair backwards. Just can't see those with the model kits. Last three, SO2. Looks like it's straight across, but when you make the model kit, it definitely is not. So it does have that bend to it, and that's important for this particular answer in its shape. So here we have oxygen up to sulfur, down to a double bond oxygen. Make sure everybody has 8. And then the last two I'm going to show at the same time because they're exactly the same. It's just 2 different ways of getting 24 electrons. So they both have double bonds to their oxygens. They both look just like their 2-dimensional structure because they are flat and they shape a triangle. Just remember that when you're flat and you shape a triangle and you have a lone pair, that changes who you are and what your shape is. So take a few minutes to think about these shapes and angles. You can record those on the last column. And we'll go to the next page. So triple bonds, we have nothing too special. Just 2 blue atoms connected together by 3 straight lines instead of 2 or 1 like on previous pages. We get into acetylene, which you can add to oxygen and cut through steel. So acetylene torches, very common in garages. Notice it too, not a whole lot different. This one's probably my favorite one. It looks like you have a sword with 2 little handles here. So it's almost like here's a little hilt, little guard for the blade. But different from a sword, it's actually more of a little gun. Looks like it goes pew pew, but it doesn't. So it's kind of like a little Marvin the Martian gun. So because it has that handle, we need to draw that handle bent. Given its name, that should hopefully make sense. 1 forward, 1 kind of in reverse. You have that lone pair, so it even looks like it's shooting little bullets out at the end. And then as we finish the last couple on this page, we have carbon dioxide. Really no different there. Looks exactly the same in the model kit. We have alene, so all double bonds here. What is unique about this one is through the middle it looks identical, but notice we do have a hydrogen forward and a hydrogen in reverse. Here we just have them in the plane. So notice this one does have a twist each time. One's up, one's back on either side. So it does have a little uniqueness to it. And lastly, not a whole lot different between sand and carbon dioxide. They're both identical, just different by sulfur and carbon. So here's those in order. Again, this one didn't really change. So now we've seen all the shapes, and we'll come back for all the polarities. All right, so in this last little portion, we're going to do polarity, and then we're going to go ahead and give you those shapes and angles that hopefully you've already figured out based on some of the model kits we showed previously. So in order to do this next column, we're going to have to look at our electronegativity table and then do the subtraction. It's just that when you have shape, you have to watch out for examples like carbon tetrachloride, which is on this page, sulfur trioxide, which is on the next page, and carbon dioxide, which is on the last page, because those have dipoles that cancel. And you'll see those everywhere in the homework. So I'll do a couple examples on each page, let you do the rest. Because in reality, all of this stuff in the beginning has been practiced on previous pages, but this last section hasn't been. So I'm not going to be as forthcoming with answers as I have been on the other columns. So again, with molecular polarity here, we're just going to take this same kind of shape and take away the lone pairs. And then find their electronegativities. So for iodine, you would go to that table and you would find its electronegativity at 2.5. And when you're attached to yourself, you're going to find out pretty quickly that the difference is 0. And if the difference is 0, you're nonpolar. The shortest distance between 2 atoms is a straight line, so again, that shape is linear. Q. The reason we care about polarity is because in cases like this next one, you have iodine and chlorine. Now if you look at that table, you're going to see 2.5 and 3.0. Now there's a difference of 0.5. So then we would draw a dipole arrow towards the bully, which is the more electronegative, the higher number. It feels partially negative because it's so electronegative. Iodine feels partially positive because it's on that positive side of the dipole, and that makes it polar. Still, the shortest distance between 2 atoms is a straight line. So those were linear. And we showed those earlier. They look like these. So try the next several, see what you think. Don't worry about polarity here, it's ionic for ammonia. Ions are superpolar. We don't have to worry about electronegativity with ions because they have overall full charges. Electronegativity looks for partial charges. So take a few minutes to complete this section and you'll be able to check the answer key later. Just remember that carbon tetrachloride, it's going to have polarity, but it's going to be a four-way tie. So hopefully you can prove that. So as we start to look at this next page, same kind of idea. Look at the overall structure, take away the lone pairs just to simplify it a little bit. We do say that if oxygen is present or nitrogen, you're probably polar, and that's true because they're two of the three biggest bullies on the periodic table when it comes to electronegativity. But here with oxygen, what's important is even though you're the biggest bully, or in this case second biggest bully overall, you're attached to yourself. And anytime you're attached to yourself, the difference is zero, and that's why you're nonpolar. The shortest distance between two atoms here is two straight lines, so it's still linear. As we go on to this next example, though, has a very similar portion. So here's that double bond for oxygen. Here's that double bond for the fruit ripening plastic bag making molecule here. So I do have that idea in the middle the same, but what's important is these are those flat triangles. They're perfectly flat, they shape a triangle. We would call that trigonal planar. And what we're going to find out very quickly in the homework and in a lot of the chapters coming up is if you're a hydrocarbon, you're only going to have C's and H's. And the reason that we can just go ahead and give an answer to any hydrocarbon is 2.1 to 2.5 is only 0.4, that's nonpolar. And 2.5 to 2.5, that's also 0, and that's nonpolar. So hydrocarbons, regardless of their size, structure, and shape, will always be nonpolar forever. You're going to see that in the organic chapter and the biochemistry chapters coming up. So take a few minutes to try the rest, and we'll come back on the next page. All right, so in this page, what we're looking for, same idea, looking at electronegativity, trying to decide whether things are polar or not. And then we're also looking for shape, which should be done already, but if it's not, we'll be working along with some of these together. I'm going to jump down. This one's attached to itself, so that should give it away. This one is a hydrocarbon, so that should give it away. But this one is unique, so let's try it. We haven't seen one as complicated as this. We've been skipping over a lot of those. So again, take away the lone pairs, look at electronegativity. So we have a 2.1, a 3.5, a 2.5, and a 3.0. So we have a small tug of war here. That's 0.5, that's a polar bond. We have a 1.0 tug of war there. That's even more polar. There's some cancellation there, but it's not perfect. And then here we have a hydrogen bonding site that we'll talk about later. That's a 1.4, significantly polar. So we have polarity everywhere. None of them are perfectly canceling. As we look at our little polarized little pew-pew gun, we have this bend shape of oxygen. Bond angle you can find on the chart, we've been skipping that. And then here, that triple bond, definitely linear. Just remember there's two types of bent. This is the bent 105, not the bent 118. Let's do one more. This one we want to do because it's going to illustrate the SO3 and the CCl4 examples from earlier. We're going to do carbon dioxide. So carbon dioxide here doesn't really look a whole lot different, but as we draw it, and this is the one that we see in lecture a lot, you have a 2.5 and a 3.5. To the left, we pull at 1.0. To the right, we pull at 1.0. Who wins? The answer is nobody. So sometimes shape can cancel your dipoles and make you nonpolar. This is why carbon dioxide, 3 times bigger than water, is a gas down to, say, negative 78 degrees. But water is a liquid, 3 times smaller, still liquid to positive 100 degrees. And that's all because of polarity. And it's definitely 2 double bonds, left and right, straight line is linear. 180 degrees. So hopefully you get some practice and hopefully you're able to check the answer keys to make sure you're on the right track. But this lab, other than a lot more busy work for you, is done.